Hello everybody! In the previous session we studied about synthesizing nanomaterials. We studied that there are two main approaches for this, and we have top-down approach and bottom-up approach. And each of them would have many various different types of synthesizing methods, and we studied some of the most important ones of them. But today we're going to study about characterization. So why is characterization important? You know, there are some vital questions that we should answer after synthesizing a material. And if we don't have the right answer for these questions, our scientific method is actually not good. It's incorrect. The first question is, have we actually synthesized what we intended to synthesize? For example, sometimes in history of laboratory and chemical reactions, you've definitely heard of some interesting stories about these things. Some scientists would accidentally synthesize some different materials, and some of them were actually lucky enough because what they made accidentally was something good and profitable. But you know, this is not something that we actually like. We want to synthesize what we actually intend to do. So the first question is, have I synthesized the right molecule? Have I synthesized the right material? And the second problem here is measuring our product's features. For example, imagine you've synthesized a nano copper wire. How would you measure its conductivity? Can you actually pick it and measure it in a circuit, in an electric circuit? No, you can't. So how would you do that? These are the problems and issues that we're facing in our scientific method for synthesizing nanomaterials. And the key answer for these problems is actually one thing: characterization methods and techniques. We can use different and various characterization methods to analyze our product. There are different types of nanomaterial characterization methods, but which one we could use? Actually, you can use any of them, but it really depends on what you need, what data you need about your molecules, about the structure, about the material that you have synthesized. In this session, we'll only talk about microscopy methods. But be careful, when we're talking about microscopy, it's not the same as the microscopes that we've seen till now. It's not like a simple light microscope, because you know, nanomaterials are super small. They're really smaller than any dimension that we can actually see with visible light. So simply we can't see them through our eyes. But what if there were some methods to picture our material? So why can't we use visible light microscopy to study materials? When our materials are in nanoscale, they're actually so small. They're smaller than the dimension visible to our eyes. So simply we can't see them with our eyes. We can't see them with normal light microscopy methods. That's why scientists made a new method of microscopy: electron microscopy. With electron microscopy, we are actually studying our material using electron beams. Okay, but how would we do that? We have this kind of electron source. As in the light source in light microscopy that we're actually familiar with, here we have this kind of electron source called the electron gun. It's similar to a gun which fires a bullet, but this gun actually fires electrons. So when this gun fires the electron beams to our material that we want to study, there can be different types of interactions the electrons have with our material. And based on these different interactions, we have different kinds of microscopy. The two main electron microscopy methods that we have nowadays are called SEM and TEM. SEM stands for scanning electron microscopy, and TEM stands for transmission electron microscopy. Let's talk about SEM at first. In SEM, we are shooting the electron beams on our material, on our nanomaterial, and we want to observe the reflected electrons. Electrons would get hit to the surface of our material and they would reflect. And we will gather those reflected electrons to study the surface of our material. This sort of microscopy actually creates a 3D shaped picture of the surface of our material. You may have seen some pictures of insects, ants, or small things that look 3D in shape. It's like you're zooming into their faces, I don't know, maybe millions of times. These pictures, which would actually seem weird sometimes, they're actually taken this way with this microscope. SEM is the microscope used in this way. So, what about TEM? How does that work? TEM, as its name suggests, is a kind of microscope which shoots the electron beam the same way that SEM did. But this time, the electron beam gets through our material. So there are 2 points that we should always consider. In TEM, our layer of material should be really thin because thicker materials wouldn't let electrons to freely move from them and move through them. And thick materials would be a really big problem because they would simply block the electrons on their way. But in the SEM, as the second point that we should always be concerned of, the main thing to consider is that our surface of material should be conductive. Because if it is not conductive, we wouldn't have the reflection happening. And you may ask, okay, in TEM we should have thin layer, and in SEM we gotta have conductive surface, but what if my material doesn't have a conductive surface? For example, it's not metallic or anything. What we do in these conditions is that for having an SEM picture of our material which is not conductive, we will simply put a layer, a really thin layer of course, of gold, silver, or any other conductive metals that could be actually put on this layer. We will simply coat our material surface with a conductive layer. So our material could be then pictured and imaged in SEM microscopy. So to conclude, I'll say that SEM is used for surface imaging and TEM is mostly used for knowing what is our material consisted of, what is inside it, what's the density of our material. These 2 microscopy methods are some of the most used microscopy methods used nowadays. The 2 other microscopy methods that we use for characterization of our products are AFM and STM. AFM stands for atomic force microscopy and STM stands for scanning tunneling microscopy. Now let's see how AFM works. AFM is consisted of an ultra thin probe which actually would go really close to our material surface. It will go really close to our material surface and it will actually measure the force between its probe and the surface of our material. As its name suggests, atomic force microscopy is a way to measure the force, the intermolecular force between the probe, the ultra-thin probe I talked about, and our material surface. As you know, there are many forces in our nature. There can be intramolecular forces like bonds, chemical bonds, ionic bonds, and there can be intermolecular forces. The forces, the attractions between different molecules and species. And AFM works based on these kind of forces. It measures the force and it relates the force to the distance between our probe and our material surface. And if you know the distance between our probe and the material, then you can simply plot the surface image of our material. And that's how a realistic image of surface of our material is drawn and pictured using AFM microscopy. Imagine running your fingers over a rough surface to feel its texture. This is the same thing that AFM does, but not on a surface, but on a nanomaterial.
So this is how AFM works basically. This mode that it works is called contact mode, and it's actually the most basic mode of atomic force microscopy. And in this mode, our probe is actually scanning through our material surface with maintaining a constant force between the probe and our material. And in this way, our probe will move upper and lower respective to our material surface. And with each of its movements, we'll actually keep track of its movement. For example, here we're doing this by applying a laser beam or anything. So this way we can actually plot our material surface, and then we would generate a 3D shaped image of our material surface doing this. As you can see, the topography of our surface is known after picturing it through AFM.
The next microscope that we're going to study is STM. STM stands for Scanning Tunneling Microscopy. In this kind of microscopy, again, we have an ultra-thin probe, the same as we had in AFM. But here, our probe is actually a conductive probe. And what we do here is that we apply an electrical field between the probe and our material. And what happens next is that whenever we put our probe so close to the surface of our material, electrons participate in an effect called tunneling. But what is tunneling? Tunneling is something similar to a lightning. You have definitely watched the lightning, and what happens when a lightning is happening is that electrons, electrical current, is flying through the air to reach another part of the clouds or the air, anything. So in here, whatever happens is actually the same. But this is not as simple as I'm talking to you right now. This is not as simple as I'm describing, but the procedure is super similar. In here, electrons actually vanish from their first place, and then suddenly they're transferred to another place. What I mean is that electrons are flying, kind of flying through the probe to our material to keep up the current in our circuit. And by measuring this current, we can actually have a knowledge about the distance between our probe and our material surface. As I said, the same goes for the STM as in AFM. In here, if we have knowledge about the distance between our probe and our material surface, we can simply relate it to the image of our material surface, and we can plot it simply.
So in a scanning tunneling microscopy, we are actually applying a voltage between our probe and our material. And as you can see, there would occur our tunneling effect, which means electrons would vanish from our probe and appear on our material. This is something like electrons flying, as I said. And via this way, we can actually plot the probe's position where we have this sort of current. And this means that there are atoms at those places where we have current actually. And after that, we will simply plot each point that we had this sort of current. And then it all depends on our material surface. So after doing all these things, there will be a plot, an image of our material surface.
So AFM and STM are two methods to plot, to picture the surface of our materials. And SEM, the one we talked before, could be used for the same procedure, but AFM and STM are actually, these two latter ones, are actually more precise in picturing the surface. So in conclusion, we studied 4 microscopies this session. The first 2 of them, SEM and TEM, used electron beams to make a plot, make an image of our material. But the second 2 of these methods, I mean AFM and STM, didn't use electron beams, but instead of that, they used some kind of probe to make an image, an informative image of our material. Be aware that these were not the only characterization methods. Actually, these are some really few ones that we discussed in this session. There are many other ways for characterization, for analysis of the material that we synthesized, for figuring out the shape of it, the size of it, and many other features of our materials. To summarize, in this session, we studied some few ways, but key ones, let's say, to study our nanomaterials. There are, of course, many ways for characterization and analysis of our materials, but these 4 microscopy methods that we discussed in this session are actually the few ones that you may study for now. I suggest that you go and study the other methods yourself. It's a really fun scientific world out there, and I encourage you to explore it. Okay, so keep exploring the tiny but mighty world of nanomaterials. Goodbye.